Yes, okay, I was muted. Sorry about that. As I was saying, is this Cox just sent me a notification that in my area they're doing something's going on. So far, nothing's happened. And I'm okay, but if we get kicked off for some reason, wait a couple minutes, log back in. I will get my hotspot going on my phone and get it back online, okay? So. All right, hope everyone had a good week. We just a couple of reminders. Next week is the first exam. We covered chapters 1 through 3. I will next Friday. We'll be done with chapter 2 and 3, and probably jump into a little bit of 4. And so next week we'll either one thing or the other. Either you can ask questions, we can work with those next Friday, or we'll just continue and jump in the next chapter, chapter 4. Okay. So it's you'll have the week here to come up with any questions if you need any assistance. So let me finish chapter 2. Then from chapter 2, I'm going to talk a little bit about the metric system. I know it can be challenging at times with respect to the centimeter, the millimeters, and so forth. And I'll talk about that. And then I have another PowerPoint that I put together a while back that I utilize to explain how we can convert literally from apples to oranges if we have conversion factors and if we follow our units and we set that up properly, okay? Because that particular technique, I think the textbook calls it a factor label method. Others call it dimensional analysis, all these fancy names for basically set up your conversion factors properly, keep track of your units, and you're good to go. All right. All right. Any questions, comments, concerns before we continue? Anything I need to address or anything like that? All right, well, if not, let me call up chapter 2. My records show we ended up on slide 23. And we just got started talking about scientific notation. Let me back it up a little bit. We were talking about significant digits. Now, let me refresh a couple of things about significant digits. Okay. You'll see, and let me share with you a whiteboard. Now, if you come across a question and the question says, all right, be aware of your answer with correct or appropriate or whatever Sig Figs, okay? So that's the question that you're asking. Now, the first thing you should ask yourself is one, and it's what is the math that I'm doing for this problem? Okay, what type of math am I doing? Am I doing adding and subtracting? Okay, or am I doing dividing and multiplying? Okay, that's what you should ask yourself first when you read the question, because that's going to determine how you treat this Sig Fig situation. Okay. Now, if you add and subtract, if the question you're attempting to do requires you to add and subtract, then we're not looking at Sig Figs. We are looking at focus on decimal. Oh my goodness, my pen just won't. Decimal places. Okay. Decimal places. That is what you need to focus on. And so if I am adding like 100.1, and I'm either adding or subtracting 1.001, then note that that first number, 100.1, only has one decimal point. And so though I do the complete math, we're adding it here. We have to truncate at the 1 decimal point. So our answer would be presented as 101.1. Okay. Because that 1/10 of a decimal position is a lot more accurate than the one at the 1,000.001. Okay. And the whole point about the Sig Fig business is that you don't present your data no more accurate than the least accurate digits that you utilized during your mathematical function, whatever you did. Okay? So the mistake, what happens is that occurs most often is you're asked to do something to give your answer, and you know you're going to add and subtract, and you start thinking Sig Figs, but don't do that. Think decimal place, because Sig Figs play no role with respect to the Sig Figs when you add and subtract. See, let me repeat that. Significant digits do not play a role when you're doing a addition or subtraction on the problem. Okay? Even though the problem says give your answer in the correct Sig Figs, I'm trying to get that corrected, but you know, it's taking some time because it can be confusing. Now, if you divide or multiply, now you think of Sig Figs. Therefore, if I take those same numbers up here, I don't know, say 100.1, and I'm either going to multiply by, I don't know, 0.1, for example, then my answer should have no more Sig Figs than the number with the least number of Sig Figs, which would be that one, because there's only one Sig Fig there. Okay, so I do the math, the division or multiplication, give me the whole digits, and then find my one Sig Fig position, and that is where I truncate. Everything to the right gets truncated. Okay, and you do the rounding rule. You look at the neighbor, determine whether the number you need where you're truncating, does it go up or stays the same. Okay, all right, so that's the main point about these problems in significant digits. So don't mix the two. So first question, ask yourself, what am I doing mathematically? Okay. All right. So then we got into scientific notation. Now this is nothing more than a method to input in your calculator very large numbers or very small numbers. Okay. Because trying to input that number, the top number in your calculator, or even that small number in the calculator, a lot of calculators won't support it. So the calculators have a format that you can input a number that is very large or very small. And once you do that, now you do whatever mathematical function you need to do to add it, subtract it, multiply, divide. Okay. So let's take this example where we have this very large number of 93 million miles, which is approximately the distance from the Earth to the Sun. Now, what we do here is stepwise procedure is we look at the number and we determine how many Sig Figs we have in that number, because you want to maintain the proper number of Sig Figs when you put it into scientific notation. So the number here is written in longhand. Okay. And we want to take it and convert it into scientific notation with the proper Sig Figs. And this one has 2 Sig Figs. Okay, so then identify where the decimal point is, and obviously this number is greater than 1, so the decimal point will be right there. Okay, from that point, since the number is greater than 1, 93 million, obviously much greater than 1, from where the decimal point is, you go from right to left and count the decimal places, and you continue until you stop right behind the last integer that you find. And so we start here and we go 1, 2, 3, 4, 5, 6, and here it is 7. So that is the last integer in this number, and that to get to that position took 7 decimal placement movements. So we write that as 9.3, notice has 2 sig figs, and then times 10 to some exponent, which corresponds to the number of decimal places that you counted. So here it is, 7. So it's 9.3 times 10 to the 7th power, which is another way to write 93 million. Okay, and that is no different than just saying it this way: 9 times 3 times 10 times 10 times 10, etc. Doing that 10 times. That's what this is telling you right here. Okay, so it's 10 to the 1 power, 10 to the 1 power, and when we multiply 10 to the 1 power times 10 to the 1 power, you add the exponent. So there's 7 of those there, so it's 10 to the 7th power. Okay. So that's how we write that. Now, the format is, for scientific notation, is important, is an integer, when I'm going to denote by, say, the letter A, better yet. It's by the letter I, whatever the integer is. Now, you may or may not need a decimal point. It depends how many sig figs you have. But then followed by a decimal point, and then followed by the other numbers, whatever number you need. Okay, but that's the format. Then finally times 10 to the exponent. I'm going to call that y. Okay, to the y power, and y represents how many decimal places you carry. So sometimes it may be written with, whatever X number of sig figs you're going to put in it. Sometimes it could be just simply the I by itself, okay, times 10 to the Y, but that is the format, okay? And so if you write it, for example, 93 times 10 to the 6th power, that would be wrong because it's the incorrect format. It wouldn't be wrong because, yes, that does represent 93 million, but it's not in the correct scientific notation format, okay? The difference between the two. It's not in scientific notation format. So it's the integer followed by the decimal point if necessary, and then whatever digits that you need, whatever they are, to give you the correct number of sig figs, times 10 to the y power. Okay. Now, when you ever are in doubt with respect to how to write your number, if your number has to be written in a certain number of sig figs, when you are ever in doubt, you can convert it to scientific notation format, because in scientific notation format, the digits are in front, give you the corresponding correct number of sig figs. Okay. So whenever in doubt, convert it to scientific notation. And I'll give you some examples of that here in a bit. All right, so that is for a number that is greater than 1. Notice the exponent. The exponent was positive. We will, for example, occasionally work with numbers that are much less than 1. For example, this number here, 0.000, etc., 17. Okay, we have to write that inside the scientific notation so we can put it in the calculator. The procedure is same, except instead of going from right to left, in this case, you're going from left to right. And so find the decimal point, okay? Step number 1, how many sig figs? Determine that. I got 2 sig figs in this number, so my answer would have 2 sig figs. Find my decimal point, count the decimal places until I find the first integer, and then stop the decimal counting after that first integer, right afterwards. So right after that first integer that you find. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so that's 10 decimal places from right to left. But because this number is much less than 1, and I'm going from right to left, that exponent is a negative. So my number is 1.7 times 10 to the negative 10. Okay, and what that, another way of writing, looking at this is basically 1.7 dividing by 10 times 10 times 10 times 10, etc. Until you got 10 tens. Okay, 10 tens. All right, so that's what we do with respect to writing numbers that are less than one decimal numbers, that negative exponent. Okay. So here they're asking you to convert these numbers into scientific notation. So for any number that you got to do that, step number one is determine how many sig figs you have, because your answer should also be in the correct number of sig figs. Okay. If we look at that first number, we have 1, 2, 3, 4, 5, 6 sig figs. Okay, so basically we're going to use all these numbers at the final end when we put it inside the notation. Identify the decimal point, which is obviously right after the 8, and then going from, it's a number greater than 1, we're going to go from right to left, and we're going to continue that until we find the last integer and stop right in front of it. So we go 1 and 2. So it's going 2 decimal places. So we write that down. It's 5.48005 times 10 to the second power. Okay. So that is that is the format for writing 548.005. We write it inside the notation as 5.48 times 5.48005 times 10 to the second power. Okay. I'm getting a signal that says my internet connection is unstable. Let us continue. All right, second one. Like we did 93 million, we're going to do the same thing here. Identify 3 sig figs for this number. So our answer obviously is going to be in 3 sig figs. We can do that right there, 6.81. Okay. Now we need to know how many decimal places. So we got 3 here. That's 3, and then 3 more is 6, and then 1 more 7. So 6.8 times 10 to the 7th power. Meters and inches, obviously. Okay. And positive, both 1 and 2 are positive numbers because, again, these numbers are greater than 1. Unlike number 3, which is a number less than 1. Okay, that tells you that my exponent would be as a negative number. Okay, identify the sig figs. Obviously, the 4 zeros up front are leading zeros and do not count as sig figs. Okay, so we got 4 0 0. So we can write that right away as 4.00 because I know that as I move that decimal point over, I'm going to stop at the first integer and stop right behind it. And so starting from where the decimal point is, I go 1, 2, 3, and 4. 4 decimal places. That becomes 4.00 times 10 to the negative 4 times. Okay, to the negative 4. Okay, now we have the number 2000, which we have only 1 sig fig. So we can write the 2 down all by itself. You just need 1 sig fig. And that'll be times 10 to some exponent. And we do like we've been doing for 1 and 2, starting from right to left. You go 1, 2, and 3. Okay, so that's 2 times 10 to the 3rd power. And that is writing the number 2000 in scientific notation with the correct sig figs. Okay, now here's an example of how you can use scientific notation to write the number in correct sig figs. So, for example, let's say you did some calculation and you ended up with the number 2000. Okay, but whatever you did over here to get that number had 2 sig figs. There was was the number with the lowest sig figs. You multiply or divided some numbers, and you ended up with 2000. And then the number with the least sig figs had 2 sig figs. So you have to present your number 2000 in 2 sig figs. Well, you can see here, there's no way you can write it longhand with the correct number of sig figs, okay? If I put a decimal point down, what makes a zero spot count? So that doesn't work. So what I got to do is put it into scientific notation, because I know that in scientific notation format, the 2 sig figs will always be correct. So here, 2.0 is 2 sig figs times 10 to the third, okay? That is the number 2000 written with 2 sig figs. And I have to write it with 2 sig figs because somewhere before, to get this number, I had 2 sig figs. Well, let's say it's 3 sig figs. Okay, no problem. Just simply add another 0. And you get 2.00 times 10 to the third, okay? That is the number 2000 written with 3 sig figs. 3 sig figs here, 2 sig figs here. Okay, and even if for whatever crazy reason you got to write it with 5 sig figs, okay, no big deal. 2.000, 1, 2, 3, 4, 0 times 10 to the third, and that has 5 sig figs. It's still the number 2000, but it's written with 2 significant digits. Okay, so that's what I meant by after you do your mathematics and you get a number, and based on what you did to it mathematically, you have to write it with an X number of sig figs, but you can't do it longhand. So what you do is convert it to scientific notation, and that puts it into the correct sig fig notation. Okay. All right. Those are your answers right there. So scientific notation always shows the correct number of sig figs. Okay, so how do we do this in the calculator? All right, it depends on your calculator. So make sure that your calculator supports scientific notation format. You don't have to get a very expensive one. The $10, $15 is sufficient. I also you can use it, during the exams, the lockdown puts a calculator there on the screen so you can use it, okay? On the browser, in the lockdown browser. But if you don't have one while you're doing other things other than exams, you can use your Windows or your Mac calculator, because will support scientific notation. Okay. So here are the 2 buttons that you may get. Let me flip to this one first, and I'll come back to that one. Now, the Windows one, this is the Windows calculator. Oh. This is Windows. I operate Windows 10. Okay. And there's a button. I use the scientific because Windows has the multiple calculators. Click the pancake, as they call it here, and select the scientific formula or calculator. And you get this calculator here. And there's a button called EXP. That is a button to put you into scientific notation format. Now, the other button you need to be familiar with is a toggle button to get you into positive and negative mode. Each calculator has a little bit different. For the Windows calculator, there's a little button here. It's +/-. So what that does is, if I type in a number and I want to make a negative, I hit that toggle button and I get a negative in front of it. So I can make the number itself a negative, or if I need the exponent negative, and I'll run through an example, I can hit the toggle button and make the exponent negative. Okay, so find the EXP button, okay, and the toggle button. Some calculators have a button, has a double E button. Okay, that is for that calculator the scientific notation format. Okay. And then the other thing, in this calculator in the middle, the toggle button for plus minus is right there. So it might look like that. It may look like the Windows, or it may be just a negative button on the button. Not the negative for you subtracting, not that one, but it may be a separate button with a negative symbol up front, okay? For your toggle button. Now, the newer calculators that I'll have a button that is, it's hard to see here, but it says X, which is times, and then 10 to the X power, okay? Now, that is the corresponding exponent, scientific notation button for that calculator. Not to be confused, I don't see it here. There's another button that is 10 to the X power. Okay, that is not the one you want to do. So in other words, you don't type in the number, then times 10 to the X power. That would not give you the correct number in scientific notation or the correct number in general. Okay, so it's not that one. So it's the symbol X times 10 to the X. Now, in this one here, the toggle button on the left, I circled here with a minus symbol, okay? Now, for all three of these examples of calculators, the format, scientific notation button is a primary button. Check your calculator. It could be a secondary button, and in that case, you know, it could be written, the one in the middle in lighter color, but you got to use the second function button, okay? So take a look at your calculator, see how you handle scientific notation. If you got the manual, you might want to read about it. If you don't have the manual, sometimes you can, Google it and you can find it. And then if you're still having trouble, shoot me an image of the calculator and we'll run through it and figure it out, okay? All right, so these are the most common buttons on calculator. So let's go back. All right, so what we want to do here is we want to input this number 2.39 times 10 to the 9th, okay? We want to input it into the calculator because we want to do some function, okay? So what I'm going to do is share my calculator, my Windows calculator, I should say. Whoa. And we're gonna input that number. Okay. And so let me write that number down so we can remember what we're doing. We're going to write down 2.39 times 10 to the 9th power. Okay. That's the number we're going to put. So you type in the number like you normally would, 2.39. Okay. Then at this point, you do not put the time symbol, okay? And then hit this button here, 10 to the actual, okay? That's not the number, okay? You want to hit the EXP button. Notice the calculator puts you into the format for the calculator. That E plus 0 tells you that is my exponent, okay? It's not going to show you the 10. Now, you might, depends on your calculator, it might write it out in the correct format on the screen, on your LED screen, depends on the calculator. But a lot of them don't have that function, and they will give you something like this, 2.39, and then the letter E, and then plus 0. And it's telling you now you input the exponent. So we simply type in the 9, okay? So what you see in the Windows calculator and in most calculators is 2.39 E plus 9. Now, if for some reason I wanted to make that a -9, that's where the toggle comes in. Okay, notice by hitting the toggle back and forth, I go back and forth. Okay, now there's another button most calculators have. It's either floating, it's called a floating point or engineering units. And what that does, it toggles you back and forth to writing that number longhand or back into scientific notation. In Windows, it's the E-E button. If I click that, notice how the number goes into longhand, okay? And then if I click it back, I'm back into scientific notation. And for relatively small numbers, 10 to the 9th, this calculator can handle that, but we'll be doing numbers up to, times 10 to the 20 plus exponent and above. And sometimes your calculator cannot handle and input all those digits. All right, now at this time, I can do whatever mathematics I need to do to this, okay? But let's say I did the mathematics and you ended up with that answer. And let's just, I don't know, let's just multiply it by 5.3 exponent 78, okay? You hit the equal, and that is my answer. So I took that number 2.39 times 10 to the ninth, and I got that. I did a mathematical function. I forgot what I multiplied it with, but that's my answer. Okay. Well, you don't report that answer. Okay, because that answer is in the format of the calculator and not in the correct scientific notation format. So let's go back to there, here, and I will input what that answer was right there, okay? Okay, now, at this point, you may get the humongous number, but here we need to determine the correct scientific notation format. So we can present that number to Canvas, and it won't accept that with the E symbol. So we're going to convert that with the correct Sig Figs. And for argument's sake, let's just say it took, the answer required 3 Sig Figs. So we at the 1, that's where we truncated. We looked at the 3 is less than 5, so 1 remains 5. So I need to do times, okay, the times symbol, then 10. And here I can, if I'm writing this longhand, if your answer doesn't support superscript, sometimes what you can do is you hit the caret, which is the shift 6 button, and then type in 166. Okay, now the answer that your calculator is now in, at least the answer in the calculator is now in scientific notation. Okay, and that's what you would present your number as 6.71 times 10. And then the caret tells you that's a superscript, and then the exponent is 166. Again, the caret is the shift 6 button. Okay. All right. So. All right, so have your calculator. All right, so you can be able to do your calculations, and let's take this problem, and you can try this at home here. While we try it, I'm going to share my
I have a question. I remember reading somewhere that you said that you can't use the calculator on exams. Is that correct? Or you can't use like a graphing calculator, I think it said.
Yeah. There's stuff. Let me put it to you this way. I don't have a problem using whatever calculator you need that has scientific notation. Okay.
Okay. I mean, you can do it easily without it, but
Yeah.
obviously if it's like 23, it's easier to do something like 23 on a calculator.
Right. And the graphing aspect of it, I can tell you why they put that in there is because I guess some graphing calculators you can program them to do all kinds of stuff. And I'm like, if you're going to spend that much time programming your calculator, you shouldn't have any problems doing the math. So it doesn't make it matter to me because I'm there, and I provide a calculator on the Lockdown browser, and whatever calculator you have that has support scientific notation is fine with me.
Okay.
Okay.
For sure. Thank you.
Okay, no problem. All right. What was happening, I think I'm going to start taking that graphing calculator out of it, because what was happening, there are some people who were able to program your graphing calculator with a variety of answers, which I don't quite follow, because some of the questions, we're doing, I don't see how you can program a chemical reaction in there, but that's not the point. So I don't know how to answer it. Just use whatever you need to do the mathematics. Okay. All right, let's do this one. In fact, to be quite honest, if you're well versed in mathematics, you don't need a scientific notation calculator to do the mathematics. If you're familiar with the division of exponents and so forth, and that's fine too. But if you're not, then obviously you need the calculator. Let's do this problem. So in this one, we are, and let me rewrite the number there because I'm sharing my calculator with you. It is 2.84 times 10 to the 23rd divided by 7.24 times 10 to the 12th. Okay, so we're doing mathematics. The mathematics we're doing is a division problem. And so being a division problem, then we think Sig Figs with respect to the answer. So we look at 2.84, 7.24, numerator, denominator, who's got the greater number of Sig Figs? Or how many Sig Figs does our answer need?
Two.
Two? Okay. Any other choices? Not quite. And remember, when we add and subtract, we think decimal places. When we multiply and divide, we think Sig Figs. And in both cases, you cannot be more accurate than the least accurate digit. So in this scenario, 2.84 times 10 to the 23rd versus 7.24 times 10 to the 12th, which number is the least accurate number? Which has the least number of Sig Figs? Okay, maybe I'll ask 2.84 times 10 to the 23rd. How many Sig Figs in that number?
Is it 3?
You got it. Okay. How about 7.24 times 10 to the 12th? How many Sig Figs there?
3.
3. Okay, so we're dividing 3 Sig Figs divided by 3 Sig Figs. How many Sig Figs should our answer have?
3.
There you got it. Okay. If
Are we
one,
not counting the Sig Figs in the 10 because of the exponent?
no, because the 10 is nothing but 10. That's an exact number.
For sure.
Okay. Remember that number 2.84 is writing it longhand would be 2.84 times 10 times 10 times 10 times 10 times 10 times 10. The 10 is not a Sig Fig. It's just, in fact, a decimal place. You're multiplying by the exact number 10. Okay. All right. Okay. All right. So your answer should have no more than 3 Sig Figs. So you keep that in mind. So do we go ahead and input the number? And we get 2.84. Okay. Hit the scientific notation button, whichever button you have in your calculator. Okay. Then we hit the exponent, which is 23. Okay. So for the calculator, that is the format for the calculator of inputting 2.84 times 10 to the 23rd. Then we divide like we normally would do anything mathematically, divide. And then put in the denominator 7.24 exponent 12. Okay. Then we hit the equal. Now what it does, it gives you, depends on calculator. Here the Windows gives you the number in all the numbers. Okay. And so I can go convert it all the way back to longhand or put it back in scientific notation. Okay, so I'm going to take this whole answer, okay, and get my mouse to cooperate. Okay. Now, that is what the calculator gave us with respect to the answer. Goodness gracious. Okay, so obviously you wouldn't you wouldn't present that whole number as your answer for two reasons. One, that number is a lot more accurate than the numbers you have to do the mathematics. Okay. You have to truncate because the numerator and denominator both had 3 sig figs. So your answer should have no more than 3 sig figs. Point number one. Point number two, the calculator gave the answer in the format of the calculator. Hence that symbol, the letter E plus 10, which represents the exponent. Okay. So what we got to do is truncate it. So we're starting from left to right. We need to truncate at the first two, okay, which is 3.92, right? Everybody agree that's where we're going to truncate the number? Or disagree, that's fine. If you disagree, let me know, please. We'll I could be throwing out the wrong answer here. Don't assume because I'm teaching and occasionally I throw in the wrong answer just to see if everybody's awake back there. Okay, and nobody's listening to me. Yes, you're correct. That's the point. That's where we truncate. So there, we put the time symbol, okay, and then the exponent, the 10 factor, and then caret 6 in the exponent, and the exponent, which will be 10, okay? So the answer is 3.92 times 10 to the 10th power, okay? And that's the way I would write it if where I put the answer in does not support superscript. But if it did support superscript, then obviously I would be writing it 3.92 times 10 superscript 10. Okay. All right. And that is our answer. So try that in your calculator. See, you come up with that same number. Okay. If you're having challenges or trying to figure out how to use scientific notation in calculator, shoot me an email and a picture of the calculator, and we'll go through it. Now, some calculators don't put that E letter. Okay, they give you the answer like, for example, like that. This one here is 1.23 4, 5, 6, 7, 8, 9, and then they put like a superscript 8. Okay, that is not scientific notation. This would have to be converted to 1.234.5. I mean, converted, but written in the scientific notation format, and then times 10 to the 8. Okay. Mathematically, these two numbers are not the same. If you write that number, okay, and present that, what this means is 1.234578 multiplied by itself 8 times, okay, which is not the number we're looking at. Okay. For example, you might think, all right, my answer is 2, my calculator presents this as 2 to the 2nd power. All right. That should be written 2 times 10 to the 2nd power. Okay. This is 200 longhand. Okay. This is 2 times 2 is what? 4. Okay. Notice totally different numbers. Okay. So make sure that find out what format your LAD puts your answer in, and then put it into the correct scientific notation format. Right. Any questions so far? Yeah.
Nope.
All right. Yeah. Did you have a question?
No, I was saying no question.
Oh, okay, all right. Okay, and then we got one last part here, which is pretty straightforward. You're probably well versed with this, you know, think of it as you take an exam, which you will be next week, right? 100 points, right? You get 80 points of the question. Boom, times 100, you got an 80%, right? And that's all it is right here. It's just a part divided by the whole times 100. For that exam, the part was 80 points, the whole was 100. Okay, well, we can use this to do any different types of calculators. For example, a ring has a total mass of 239.45 grams. Underwent analysis, and it comes back and says that of that 239.45, 198.3 grams of it is pure gold. Okay, calculate or determine the percent gold in this ring. So identify the part, which is 239.45. Identify, excuse me, that was the whole, and the part is 198.38. Okay, times 100 gives you the big old number 82.84819, etc., etc. Right? That would be incorrect to give your answer in that format. Why? Because your Sig Figs determine your answer. So your numerator has 5 Sig Figs, your denominator has 5 Sig Figs, therefore your answer should have 5 Sig Figs. So your calculator output this number, you go to the 5 Sig Fig position, which would be right here, the 8. Okay. And now you look at the namer like you normally do. It's a 1, and you do your rounding, so the 8 stays as an 8. And now your answer is 82.848%. All right, well, what that does, congratulations, ladies and gentlemen, you have suffered through 2 chapters, or suffered, tortured through 2 chapters of chemistry. Okay, any questions?
Can we take the exam sooner than next Saturday? Or is it only, do you open it the
Yeah,
night before and
yeah.
then it's only open for one day?
Yes, exactly. So,
No
and
worries.
yeah, so we still got one more chapter to do, so.
Okay.
Okay. But before I proceed with the next chapter, we're gonna get into some calculations, specifically converting units from one set of English units to metric units, and we're gonna be talking about a procedure and how we do that. Let me just introduce you about the metric system to kind of refresh my memory here, because you may have had this before someplace somewhere. We've been trying, the US has been trying to convert to the metric system since I was in elementary school, so that's like 100 years ago. We're still not there, you know. You can go and get a gallon of milk at the grocery store, but if you want to buy a soda pop, you get them in 2-liter bottles. So we do a mix and match kind of thing. All right, well, let's talk about the metric system, as far as the units that we utilize in science here. For mass, we use the symbol G for gram. In general, that is the main symbol, most common symbol that you would use, G for grams. The volume is a capital L for liters, and the length is lowercase m for meters, okay? Now we use prefixes, okay? So we can go put a prefix in front of our symbol. If we put the prefix K, that tells us kilo. The prefix is a kilo, which means it's 1,000 times greater than what the letter we're putting in a prefix is. So what that means is, for a gram, there are 1,000 grams in 1 kilogram. Okay, we can do the same thing for the liter and call it a kiloliter. And what that tells you, there are 1,000 liters in 1 kl. Okay, and a kilometer, again, there's 1,000 meters in 1 kilometer, one click. Some people use the term click. Anyway, now let's take a look at grams, our base unit here for mass. If there's a prefix called centi, okay, hence the letter D. There's a prefix called centi, hence the letter C. Milli for M for milli, and then the symbol looks like a U with a little thing in front of it. That is called micro. Okay. Now, one way to remember this is for, I think of it in the beginning, I was like, okay, D for decade, because I know that there are 10 years in a decade, hence there are 10 decigrams in 1 gram, okay? For centi, there are 100 years in a century, okay? Therefore, there in 1 gram, there is 100 centigrams. And in a millennium, there are 1,000 years in 1 millennium. Therefore, I have in 1 gram, I have 1,000 milligrams. And then the micros, probably you never heard of that one, but micro, there are 1,000,000 units in 1 gram. So there are 1,000,000 micrograms in 1 gram. Now, those prefixes for mass can now be used for volume. Okay, so in 1 liter, there are 10 deciliters, 100 centiliters, 1,000 milliliters, and 1,000,000 microliters. Okay? And we take the same prefixes and just move them over to the left. There are in 1 meter, 10 decimeters, 100 centimeters, 1,000 millimeters, and 1,000,000 microliters. Okay, so the units in metrics are pretty straightforward, pretty interesting. Now, what this does is this: each one of these has. Each one of these are a conversion factor that you can set up as a ratio. For example, taking the kilogram and 1,000 grams, I can write it 1 or 2 ways. I can write it with kilogram in the numerator and 1,000 grams in the denominator. Or I simply invert it and put 1,000 grams in the numerator and 1 kilogram in the denominator. Which one I use, obviously these conversion factors, I'm going to multiply by some value, okay? And so here, for the one on the left, if I start off with units of grams, and I want to get to kilograms, then I will use the factor on the left. Why? Because if you see, look at this, my grams cancel. I'm keeping track of my units, my grams cancel. So if I want to go to kilograms from grams, then I'm using the factor on the left. If I start off with kilograms and I want to go to grams, then I use the factor on the right, because my units of kilograms cancel when I multiply. And this is what we mean about looking at your units, keeping track of your units, because down the road, when we do calculations, we are going to use multiple of these factors, okay, to get to the answer that we're looking for, okay? And by keeping track of your units, you can just simply cross out your units, and that would tell you whether you set the problem up correctly. Now, here, you might be tempted to, let me clear my mess up a little bit here, when I use these conversion factors to convert the coefficient or the number that comes with it. Like the 1,000 here, you can, convert that 1,000 to a fraction. My recommendation is this: leave the numbers alone. Just stick the 1,000 in the denominator, leave it at that. Put it in the numerator if you need it, leave it at that. Don't convert it to give you 0.001 kilograms in a gram, because down the road it could confuse the issue. Okay. Second of all, when you start setting up your problems, once you get your answer, look at the answer and think about what you did to it mathematically and unit wise and value wise. Does that, the way it was set up, was it set up properly? Okay, because let's say, for example, I'm using the factor on the right and I multiply by 10 grams. Okay, well, look, check out my units here. I got grams times grams divided by kilograms. So my units, just the units, would be grams squared divided by kilograms, which doesn't make any sense at all. Okay, unit wise. You're always going to end up at the end with 1 unit. Okay, so that in itself, by checking the units out, tells you, oh, I set this up incorrectly. I should use the one on the left because my units cancel out properly and I'm looking for units of kilograms. All right. For example, we have a problem here. It says, how many micrograms are in 0.0125 grams? Well, we start off by writing down what we're given. And that is what we're given, kilograms. And I write down at the other end what units I'm looking for. I want units of micrograms. Obviously, I don't have the value, but I know what units I'm looking for. Why is that? Because now I know what factors I need to put up here to get me to those units, okay? The first one, I need a factor that puts kilograms in the denominator, okay? And in some other unit on top here, so I can get rid of kilograms. So I go over here to my table and start looking at, what can I use here? All right, so let me show you here. Oh, come on. All right, so my first one, that was what I'm given. These are the units I'm looking for, okay? And I know from my table up above that there's 1,000 grams in 1 kilogram. So I know I need to put kilogram in the denominator because that cancels out, which leaves me with units of grams in the numerator. Okay, no problem. Look for another factor that I know has grams in the denominator, because that's going to cancel out when I do the mathematics with respect to my units. Leave me behind the units of micrograms, which is what I am trying to determine. So keeping track of my factors here in units allows me to set them up properly. Now, I guarantee you, if you follow this system, that 99% of your answers will be correct. I cannot say 100% because I don't control the calculator. You do that, okay? And so now it's just simply a matter of 0.125 times 1,000 times 1,000,000, and I'm good to go. Now, once you become proficient and you become, comfortable with this, you can see that I can combine these factors into one, okay? But if you don't see that right now, don't go that route. Just do each one individually until you're comfortable about actually combining factors together into making one factor. A lot of times the question asks you says to show work, okay? Well, this is what we mean by showing work. By showing us how you got from point A to point B. Because we can, for example, this could be worth, I don't know, let's say this question could be worth 5 points, okay? Well, the answer could be 1 point, and then the remaining 4 points are over here. And so if you just give me an answer like that, then the only thing I can give you is 1 point for your answer, because you didn't show your work, okay? Also, it does happen that you set it up properly and everything lines up, but for some reason, you mathematically in your calculator, you write the wrong answer. 135, for example, which is the wrong answer. Well, obviously, I can't give you the point for that because the answer is wrong, but I definitely will give you the 4 points, okay? So that's what we're talking about. So what we mean by showing your work, if you have to do that in any of the work that you need to do. All right. we do give you these factors, they're in the shapes table. And these factors are to convert from inches to centimeters, okay, going from English to metric. And then we got 2 units more conversion factors to get you from pounds to grams and quarts to milliliters, okay? So here, the thing about these 3 factors are this factor by convention is treated as an exact number, okay? And these are not exact, your measurements. So what this means is that the 1 inch to 2.54 centimeters would not be a factor in determining your Sig Figs if you're using that factor, okay? It wouldn't be a factor. However, the other 2 factors could play a role in determining the final Sig Figs if you use those last 2 factors here. So keep that in mind. These 3 factors, again, can be written up in the ratio, written 1 of 2 ways, as we show there. Okay? And allows you here to get from English to metric units. And this is true for any conversion factor, any ratio, okay? Because we're going to use this system down the road where chemically, let's say we got A plus B gives me C, maybe 3 C's, maybe 2 C's. Well, there's a ratio here of 1A to 2 B's. And we're going to be using, we could use this ratio like that, or A in the numerator, okay? And we're going to be comparing reactants here to do some calculations, all right? All right. All right. And some basic algebra review, nothing complicated, just keeping in mind that, you know, if we are dividing like terms or you know, the terms can cancel out, or if they're not like, they continue, like density, for example, you know, density normally is grams over milliliters, okay? So those are the units of density, all these grams are over milliliters. Here, when we're multiplying like terms, you know, so it's 8 times 8 gives us A squared, okay? And we're dividing by A, we can divide it as follows. So just a general review, go back and refresh your memory about being able to do some general chemistry, general algebra, nothing complicated. Okay? Because we'll be looking at units. All right, now what I want to do is, before we jump in that chapter, is to give you an example of looking at units. And this one here is called dimensional analysis, the technique, which is also the factor label method, same thing. I had set this up to demonstrate when I was teaching in Carrington part-time. I was teaching my dental hygiene students. I was trying to demonstrate how to use this method to go, and as an extreme example, to go from crazy units, from bananas to oranges. Specifically, what I was saying here is, all right, given the following conversion table factors, 1 DH is equal to 6 grapes, etc., determine how many dental hygiene students is equal to 4.5 bananas. And on surface, it's like, well, that's crazy. And my response is, no, if you got conversion factors, you can do it, okay? So those are my conversion factors. Okay, 1 DH is equal to 6 grapes, 3.5 grapes to 1 orange, 1 orange to 6 toothbrushes, 3 toothbrushes to 1 banana, okay? Using that information, setting up my units properly so they cancel out, I can set it up and just do the math to determine exactly how many DH students are equal to 4.5 bananas. So writing what I'm given, I got to go from 4.5 bananas, and I write that down on paper or whatever I'm doing in my work, so I know where I'm going and where I'm at, I should say, and need to know where I'm going with respect to units. And that allows me to set up my factors in between here Keeping in mind that I start off with bananas, I'm gonna have bananas, my first factor is gonna have bananas in the numerator, okay? And then some other factor on top, which then eventually I want to get rid of, so eventually I'm gonna get rid of all of my units, so I have DH units at the end, okay? That is the goal. So let's walk through it. All right, so here's the conversion factors. And here's my first one, okay, where I'm giving 4.5 bananas. Keep it in mind that way down here, I'm looking for DH. Okay, so that's keeps me on the straight track to know where I gotta go. All right, so when my first factor, note that bananas cancel out, which is perfect. But now unit-wise, I'm left with toothbrush. So I'm not where I need to be with DH units. So I need another factor to get rid of toothbrushes. And then looking at my conversion factors, I have one there where I got 6 orange and 6 toothbrushes. So now, keeping track of my units, we see bananas cancel, toothbrush cancel, leaving me at this point, if I needed to stop the calculation, I would know how many bananas will be equal to how many oranges, okay? If that was the question, I could stop it there. But I'm not, because I gotta go to DH2. So I need another factor. And that factor is the grape to orange relationship, okay? Again, keeping track of my units, canceling things out as I go along. I'm now in the units of grapes, so I can go from bananas to grape, wise. But again, I'm not where I need to be. So I continue. And I have finally, at the point with respect to units, okay, I'm not even pushing the numbers yet. Okay, I'm just keeping track of my units. And now I am unit-wise where I want to be, where I relate 4.5 bananas to DH. Now everything's set up. Notice that I didn't convert the numbers I'm given. I just left them as they are and just put them in numerator and denominator as needed. It followed the 6 toothbrushes. The 6 follows the toothbrushes, whether it be in the numerator or denominator. Okay. But now we just do the math. And once we're done, at the end, it equals to 4.5 bananas is equal to 1.3 DH students. Okay, so that is an extreme example, but that's the point. Okay, to give you an extreme example where you literally got apples to oranges here. Okay, but given the factors, you can do that. And I made it an extreme example because sometimes when we get to chemical reactions, you might feel like that. I'm like, wait a minute, how do we get to, if I have 10 grams of sodium bicarbonate, how many grams of carbon dioxide I'm going to make in this reaction, okay? It feels like on one end you got the bananas and the other end you got the DH students. But once you put everything together with the proper units, and we're going to go through this stepwise and systematically to, become comfortable with this, okay? So that is my extreme example. All right. So what I'm going to do now, I got 240, almost 245. Let us take a quick short break. Okay. That PDF file that I went over with the metric units and even this extreme example, I did upload that. I believe it is in module 3 for this chapter. All those documents should be in there. So feel free to go through them, and if you have any questions, email me or bring it up next Friday. So let's tell you what, let's take a quick 15-minute. Okay. Then we'll jump in through chapter 3. It's very relatively short chapter. We're basically going to be converting units. We're going to use this technique of keeping track of the units. And factor label is what your book calls it, or dimensional analysis. And then we'll go from there. Okay, it's short, relatively short chapter, 27 slides. All right, so let me pause Okay. Welcome back. All right, any questions, comments? At this point, I will, if not, I will continue now with chapter 3. Okay, chapter 3, where we're going to be dealing with some mathematics, nothing complicated. We're going to mostly multiply. All right, metric units and conversions. As I mentioned earlier, the symbols for length, mass, volume. We're not going to use too much of time, but time is second with the symbol S, M, lowercase m for meters, and lowercase g for grams in mass, and capital L for liters in units of volume. Okay. Now, the prefixes, which I introduced in that PDF file, dealing with the symbol K for kilo, which represents 1,000 times larger. Okay. D for deci, 10 times smaller. C for centi, 100 times smaller. M for milli, for 1,000 times smaller. And then the mu symbol, that's the lowercase mu, Greek symbol mu, for micro, which is 1,000,000 times smaller. Okay. And so a meter, we see here, a meter is equal to, we see the units of cm, meaning centimeter. Centimeter to me is 100 years in a century. Therefore, there are 100 centimeters in a meter. 1 meter is equal to, I see dm for decade, 10. So we got 10 decimeters. And then 1 kilometer, which is 1,000 times larger, means that there are 1,000 meters, okay, in 1 meter. And then obviously a million micrometers in a meter and 1,000 millimeters in a meter. Okay. So it's all there for you to help you out with respect to converting from within the metric system, but also utilizing these conversion factors to go from the metric into the English or vice versa. All right, so we utilize what is called the factor label method or dimensional analysis. Call it whatever you want to call it. Keeping track of your units. So what we do is we look at the question and identify the units that you are looking for, what you're trying to find. What is the units? Okay. I'm concerned about the value at this time because we're going to plug those numbers in the calculator and get your value. So we're just focusing on the units. Okay. We identify from the question what you are given. And most of the time you're given not only value, but units. So, and that helps you to determine what factors I'm going to utilize to get to the final unit that I need to get to. Okay. And then we multiply all these factors and set it up so that the units cancel out. Okay. Check the units and then make sure that the number at the end has the proper number of Sig Figs. And since we are multiplying, again, here, when we multiply, we're thinking in terms of, okay, no worries, you got to leave, no problem. I just saw your message there, Jessica. Yeah, okay, so, all right, so the best way to do this is to do something again, all right? Keep track of your Sig Figs at the end. Now, in this question, it says, all right, how many liters are in 2,389 milliliters? So we can see that we are staying within the metric unit. So we don't have to do any conversion factors to go into the English or vice versa. So we write down what we're given. Okay. Milliliters. And then I write down the units that I'm looking for. Okay. Now, check out how many Sig Figs we have. So we got 4 Sig Figs here, which means our answer should, since we're sticking within within metric units, our answer should end up with 4 Sig Figs. And I say that because within the units, Conversion factors are exact numbers and would not play a role in determining sig figs. Okay. I also know that based on my table that in 1 liter, there are 1,000 milliliters. Okay. So I set this up with milliliters in the denominator. Why? Because I want milliliters to cancel out when I multiply by this factor. And I want liters to be in the numerator because those are the units I'm looking for. So now it's a matter of just plugging in the factors and numbers. And I'm good to go. Now I do the mechanics. And I should end up with 2.389 liters. Okay? 2.389 liters, which is in the correct number of sig figs. This is an exact number, so we're not play a role in your sig figs. My factor, and there's my answer. Okay. Also think about the number. Does the number make sense? All right. Does it make sense? Because just looking at the value of the number, and just the number, the value number, you are taking a number in the 2000 range, you're dividing it by 1,000. And so the final number you're going to get is going to be much, much less than what you were given. Value, just the value within the number, right? If you inadvertently multiply this by 1,000 instead of dividing, then, you know, because it has happened where people have put in 1,000 liters in 1 milliliter. Well, think about that. First of all, if you use that factor, does it make sense that there's 1,000 liters in one milliliter? Okay, doesn't make sense at all, because we know approximately what a milliliter or what a milliliter is if you ever use liquid dispensers to dispense medication, a small amount. And the liter is a large quantity, 2-liter bottle of soda. So this itself would make sense. But even if you multiply that out, you end up with a humongous number. And that wouldn't make sense at all, again, since you're going from milliliters to liters. So think about the answer. Does it make sense? Okay, just don't rely on the fact that, boom, a calculator gave me that number. It must be right. Okay. All right, in this one here, we're asked to calculate the number of kilometers in 12,300 centimeters. So 12,300 centimeters, okay? And we need to get to the units of centimeters. All right, so I'm going to need factors here. Probably about 2 of them. Okay, and what do I know? What connection do I have? Well, if you go back to the table that we talked about earlier, we know that in 1 meter there are 100 centimeters, right? I use that because I start off with centimeters. So I'm going to need a factor. Oh, I made a mistake here. I need to go to kilometers, okay? I wasn't paying attention. Those are the units I'm looking for. I may be thinking kilometers, but I was looking at cm. And so this first factor will get rid of my centimeters. Okay. Now I'm in meters, but I need to get to kilometers. So what do I know about kilometers, the relationship between kilometers and meters? I know that there are in 1 kilometer is 1,000 meters. So therefore I put 1,000 down at the denominator. Why? Because I want my meters to cancel, leaving me with units of kilometers, which is what I'm looking for. So with respect to my conversion factors, by following them through, I got it set up. Now my recommendation is this. I know I see this every semester. And I try to tell students not to do it because it can get, if you don't do it properly, it can send you out there in left field. And, we all know about the ratio system. We can do this. All right, so you got 3 knowns and 1 unknown, and then create a whole new ratio and keep going with that. That can put you off someplace where you don't want to go. So my recommendation is not to use that, okay? And use this method here where you put multiple or conversion factors in there and just follow your units, okay? All right. Let's clear this up here. That up, here's what I'm given. These are the units I need to cancel things out, okay? Notice my centimeters cancel, my meters cancel, living in the units of kilometers. And I want to go from a large number value-wise, and I'm dividing by numbers here. So this number at the end should be much smaller than what I started off with, and that's the case, okay? If I start off with a number much, much greater than what I started off, that means I multiply by 100 and 1,000, and I divide. So give your answer some thought. All right, these are English conversion factors. Okay, which again, in the way they're written, it's a ratio. So I can, put cups in the numerator or cups in the denominator. And this is by no means a complete listing. If you have more, feel free to use them. I mean, you can go 5,280 feet equal to 1 mile. Okay. Or you can say 36 inches is equal to 1 yard. This is what I mean by combining factors. Okay. So whatever works for you. All right. I've always had trouble with the English units and trying to get pints and cups and quarts and everything straightened on my head. So this little thing kind of helps out. It's in your that PDF file for your reference. So what you see here is the big G on the outside, which represents the gallon. And then within the gallon, there are 4 Q's, which represent the quart. So that's 1 gallon. 1 gallon is equal to 4 quarts. Now within the quart, there are 2 P's that represent the pint, which is equal to 2 pints to 1 quart. And then within the P, there are 2 C's that represent cups. So 2 cups to 1 pint. Okay. So here we got 3 conversion factors. And if you can combine into one depending on the unit that you're looking for. But if you don't see that, then definitely use them all separately. Okay. For example, the question here says, how many gallons are in 4.5 cups? All right. So we write down what we need to get, what we're given, I should say. And then I also write down what I'm looking for with respect to units. Okay. So I got cups here. So I find a factor that will eliminate the cups and get me into a different unit, and that is the 1 pint to 2 cups. So that takes care of my cups, but I'm in the units of pint. So I need my other factor to get rid of pints, and this one gets me into quarts, okay, unit wise, which if that's what the question for, I can stop it right here. But then obviously I need one more factor, and that is the relationship between quarts and gallons, 4 quarts to 1 gallon. And so I looking through all this, looks like everything's canceled out. Okay. This, by the way, is, if you think about it, I can also make one conversion factor to 1 gallon is equal to 16 cups. You don't see that? Using all this inside, gallon to cups. Pints cancel, quarts cancel, leaving me gallons over cups. 2 times 2 is, 4 times 2 is 8, times 2 is 16. So this factor is perfectly okay to use, okay? But if you don't see it, by all means, keep them separated until you're comfortable with the system. And then looking at my Sig Figs, my answer should have 3 Sig Figs because all those factors inside are all exact numbers. Okay. and wouldn't play a role in Sig Figs. This one here, we're going from inches to yards, so I write down what I'm given. I also write down the units that I'm looking for, so I keep track of my conversion factors. I got my first factor here that gets rid of the yards. Okay. And puts me into units of feet. Okay, I'm not in yards yet, but I can put in one more factor, which then goes from inches to feet. Oh, I was wondering what I did here. I'm paying attention. I need to go through inches, not yards. Start off in yards. Okay. All right, and now I just do the math. So I get 126 inches. Now I ask you the question, can I present my answer as 126 inches? Would this be correct to give that as an answer? What do you guys think? You might think, well, that's the answer I got on my calculator. That is correct. If I take 3.5, multiply by 3, and multiply that by 12, I do get 126 inches. But would that be the correct answer to give with respect to Sig Figs? Anybody? What we got? No, it should be, Jonah, you're correct. It should be 130. And actually, you're also correct, but not 2. I'm not sure of your answer, actually. Okay. Keep it in mind that we got, oh, I see what you said, 2 Sig Figs, my correction. So I got 2 Sig Figs over here. My answer should be 2 Sig Figs, so I need to look at the second significant figure position, which is the 2. I look at the neighbor, which is 6 greater than 5, therefore the 2 becomes 3. And I make sure that 6 gets converted to 0, okay? Not dropped, right? You don't want it to. Oh, okay, no worries. All right, but you don't want to drop because, remember, you're in the hundreds. Your magnitude is in the hundreds, 126, right? And if you drop that 6 to 0, guess what? You get to 13. And so if you don't see that, put a dollar sign in front of it, okay? You're 130, you're still in $100 range. That's what you started off with, in the hundreds. Okay. If you drop that 6, you got $13, which is quite a bit of difference, right? Factor of 10 difference. So that changes the magnitude. So don't forget about that part. That 0 part. Where numbers before the decimal point get converted to zeros, and that drops. All right, good. I did mention this before with respect to Sig Figs. 1 inch at 2.54, it is treated by convention as an exact number and therefore will not play a role in determining Sig Figs if you use that factor. However, the other ones, 454 grams and 946 grams, are approximate numbers and therefore will play a factor, could play a factor with respect to Sig Figs in your final answers, okay? In fact, some of the questions in the homework use these factors, and it turns out that the answer with correct Sig Figs is determined by these factors, so be aware of that, right? And of course, you're given these factors because they're in the shapes table. You look at the shapes table, they're sitting up on top, so you don't have to write them down any place, they're sitting there. All right, now using those factors, we are able to go from the English to the metric and vice versa. So here, we're being told to go, we have 248 grams, okay? And we need to go to pounds. All right, so we need a factor to get rid of grams. And we know one of the factors is 1 pound is equal to 454 grams. Okay. In both cases, the 454 could play a role. It's not an exact number. It has 3 Sig Figs, and the 248 has 3 Sig Figs. So our answer should have 3 Sig Figs. Okay. So 246 grams is equal to 0.546 pounds. All right. Here's one here that's a little bit kind of interesting. Okay. We're looking for inches and we start off with kilograms. Okay. And so we go 354 times 10 to the negative third kilograms. So here's an opportunity to utilize a scientific notation format in your calculator. And we're wanting to go to inches, okay? And so I need conversion factors to get me out of kilograms, because I know that 1 inch is equal to 2.54 centimeters, okay, for my conversion factor. And I also know that 1 meter is equal to 100 centimeters. Okay, so that connects the inch to centimeters back into the metric, but I'm in kilometers, so maybe I need one more where it says kilometers is equal to 1,000 meters. Okay, so let's think about it. We're in kilometers, and this first factor here gets us into meters. Okay, and so we can write that one here. So we got right, K, it's km, kg. And so I put kilometers in the bottom, that's 1, and it's 1,000 meters in the numerator. Okay, keeping track of my units, see my kms cancel out. Now I need one more factor to get rid of meters, and that puts me into centimeters, because I know that 1 inch is equal to 2.54 centimeters. So I put 1 meters in the denominator because I want the meters to cancel, leaving me with 100 centimeters in the numerator. Okay, so at this point, I could end up with centimeters unit wise, but I got to go to inches. Obviously, inches is going to be in the numerator because those are the units I want. And then obviously, I want to get rid of centimeters, so that goes in the denominator. Right, so I got 1 inch. And then 2.54 centimeters in the denominator. So CMs cancel, meters cancel, kilometers cancel. I'm at unit wise, I'm at inches. Everything seems to be set up properly. Now it's a matter of you plugging in the numbers into the calculator. Let me clear this up a little bit. And I end up with 139 inches in 3.54 times 10 to the negative third km. Remember, that is 10 to the negative third km. So when you put that in scientific notation, you want to make sure that you toggle that exponent, and that would be as follows. Let me share the calculator. And so 3.54 exponent 3 toggle, okay? That is the number 3.54 times 10 to the negative third in the Windows calculator. Don't forget to toggle the number. All right, 2-liter bottle. I want to know how many quarts, okay? So we set that up. We're given liters, we want to get the quarts. So we know then 1,000 milliliters is equal to 1 liter, so that takes care of the liters. And then from our conversion factor, that 1 quart is equal to 946 milliliters. That gets rid of the milliliters, and now it's a matter of just typing into your calculator, keeping track of your Sig Figs. And notice here, we start off with 2.0 with 2 Sig Figs. Remember that this conversion factor could play a role, but it has 3 Sig Figs. So I'm saying our answer would have 2 Sig Figs. But if, for example, we started off with 2.000 for whatever reason, which has 4 Sig Figs, then our answer will be determined, as far as Sig Figs, will be determined by the 3 Sig Figs in 946. Okay, so that's, I'm just wanting to give you a heads up. So pay attention to those 2 conversion factors when you utilize them in your calculations. All right, so practice. You got an exam obviously next week and so forth. Try not to Google your own conversion factors. Use our conversion factors, and we say that because Canvas answers are based on the conversion factors we give you. There are thousands of conversion factors out there with a different number of significant digits, and when you use those and plug them in, it could change the value that Canvas recognizes as a correct answer. Not to say it's incorrect, but Canvas will treat it as incorrect, and then you won't get credit for it. Okay. That being said, I will always, if you think that your answer is correct and disagree with what Canvas says, shoot me an email, tell me what question, what assignment. I have no problem with going in there and checking it. Okay. Be careful when you input your answers, because Canvas will treat a space, okay, as a number. And if your answer is 2.0 and you say you type in 2.0 inadvertently hit space, Canvas will treat it as incorrect. All right, so, or if you inadvertently add any other character in there that shouldn't be there, or put a space in front of your answer. Canvas is definitely not AI. All right, so we're working to make sure we can teach it to learn all the possible combinations that people could enter and answer that is correct, but enter it wrong. All right, so with that said, kind of shift gears a little bit. We're going to talk about volume by displacement. We're going to talk about get into doing what are called density calculations. We did introduce density, where it's the mass over volume. And there's a couple ways that we can use density in these type of calculations, okay? But let's talk about volume. Well, volume are, 2 ways to get volume, to obtain volume. If you have a nice, even rectangular, square shaped chunk of matter, you can simply just measure length, width, and height, and that gives you a 3-dimensional measurement, which is volume, right? In either a cubic centimeters or whatever units you use, but we can convert that to milliliters. Another way, if your piece of material has an irregular shape and you cannot easily measure the volume out, you have what we call volume by displacement. And it's straightforward. Think about this. You're in the bathtub, the bathtub or in the jacuzzi, okay? And that has an X amount of volume. The moment you completely submerge yourself in that jacuzzi, doesn't the volume go up? Yes, it does. It goes up because you displace an X amount of volume based on your body, okay? Now, if you have a way to measure that volume of that jacuzzi before you jumped in, okay, and they just say it's 200 gallons, for example, and then you jump in and maybe it's now you have somebody measuring it where you're completely immersed, and now the marking goes to 210 gallons. Well, it's kind of extreme example, but the difference is your volume. The difference is the volume that you displace. The 210 gallons is not your volume, okay? What you displace between the ending point and the final point is what your volume is. And this is kind of trying to demonstrate it here, where you have a diamond and you put it in a graduated cylinder, which is basically just a cylinder with markings. Okay, that it's a way to measure, a tool we use to measure volume. And it has a base here and it's got the markings to measure volume, okay? And so if you start off with, 20 milliliters of liquid, sometimes water. So it starts off there, you measure it, okay? Then you throw the diamond in there where the diamonds fall to the bottom. And then the new volume is now 34.7 because that diamond displaced that liquid and pushed it up, okay? So the actual volume that diamond has is the difference between where it ended and where it started, which in this case would be 14.7 milliliters. That is the volume of that diamond. Once you know the volume of this diamond and you know the mass, we're going to take that information and we're going to take mass over volume. We're going to calculate the density for that, for any material. Okay. All right. So the important thing here is if you're doing your calculations, which we will, and you come up across this example, please don't use this 34.7 as the volume of the diamond, because that is not the volume of the diamond. That is the final volume that the diamond displaces. And the actual volume of the diamond is the difference between where it finally displaced from where the volume began. Okay. And so that diamond has a 14.5 milliliter volume associated with it. Diamonds made of carbon. This carbon is a solid. It's asking you what's the state of matter of this element. Okay, now how do we calculate the volume of, let's say, a rectangular box? Well, it's length times width, which gives us area. But given the depth, we can now calculate the total volume. Okay, so in this case, we have a little shoe box that's 24 centimeters by 11 by 16. We now have a volume of 4,200 cubic centimeters. Now, if you recall back a while back, we mentioned that in 1 milliliter, there is 1 cubic centimeter. That was a conversion factor. All right. So 4,200 cubic centimeters is also equal to 4,200 milliliters. Okay. I convert that to milliliters because density, we're going to learn the most common units of density are grams over milliliters. Not to be said that you could use cubic centimeters, in some cases you can, but the most common units are grams over milliliters. Okay, and that is what we're going to talk about. This is the most common units used in density, which is the mass over volume. Okay. And think of density as basically how much matter is in a given space. All right, let me clear this up a little bit. Okay, solid is the most dense, okay, of the states of matter, whereas the least dense is gas. So you can see here by the density, which is in this case the units of grams over cubic centimeters, which is also millimeters. The density of air is much smaller than the density of, say, gold or most solids. Okay. Now, the density calculations can be done one of two ways. The first one is real straightforward, where we're simply are dividing the mass that we're given by the volume. Okay, Now, excuse me. Okay. Something all of a sudden made me want to sneeze. Another way is taking the density of a compound. We can use that density value to calculate either volume or mass of that compound. For example, chloroform has a density of 1.48 grams per milliliter. Now think about that ratio. That means for every milliliter, okay, this ratio right here, for every milliliter that you would measure out in with a volume dispenser, it would weigh 1.48 grams. Okay. The same token, for every 1.48 grams of chloroform that you weigh out, it would have a volume of a one milliliter. Okay. All right. So we can either going to just calculate by type 1, where we just simply divide the mass by the volume. The volume is something that we could measure by displacement, or actually measure length, width, and height. Okay. Or we could be given the volume in liters, and we need to convert it to milliliters, hence the conversion. So that density is, guess what? Another ratio. And being a ratio, we can write it with grams in the numerator or invert it with grams in the denominator. Okay. Which one we utilize depends, like we've been showing, on the question. The one on the left, we're going to be multiplying by volume to give us units of grams. The one on the right, we're going to multiply by X grams to give us units of milliliters, because grams cancel. Now, when you do these type of calculations of type 2, you should always end up with a single unit, okay? Unless you are calculating a type 1 where you're actually calculating the density, and only then do you have units of grams over volume. But for the type 2, you're either going to have units either in milliliters or units in grams, not that ratio unit, okay, of grams over milliliters. Right. For example, what is the density of this necklace that weighs 484.56 grams, and it has a density given to you of 25.64 milliliters? Well, we simply just take the equation, okay, plug in the numbers, okay, and then do the math. And then finally at the end, do keep track of your Sig Figs, because the denominator here has 4 Sig Figs. The numerator has 5 Sig Figs. So our answer should be should have no more than 4 Sig Figs, because the 4 Sig Fig was the least accurate number. Okay. All right. So here, that necklace has a density of 18.90 grams per milliliter. Grams per milliliter. All right, let's do some calculations using chloroform as an example. Chloroform, FYI, was the old way they used to use to knock you out when they put you under for operations. I remember as a kid doing my tonsils, they put a mask on me, and then they dripped in some chloroform, and next thing I know, I'm spiraling, and it's just, I'm out. It knocked me out. Give me a bad headache the next day. All right, so here, the density of chloroform is 1.48 grams per milliliter, okay? The question is asking you, how many grams would 17.5 milliliters of chloroform weigh? Okay? So, like the problems we've been doing, we write down what we're given, okay? And we write down the units that we're looking for, okay? Now, by following the units that you're given, you can set up your conversion factor here correctly. We want milliliters in the denominator and grams in the numerator. Okay, because we want milliliters to cancel. And therefore, I simply multiply by the 17.5 milliliters by the density, giving me the number of grams of chloroform. Okay. And let me clear this. And that. And so 17.5 milliliters of chloroform will weigh 25.9 grams. And we use the density a lot in the lab because sometimes we actually cannot, maybe our balance, we don't have a balance and it's not working. And so the only way we want to take this liquid out, we need an exact number. We need 25.9 grams. Well, we can get a volume or a regular cylinder and measure out 17.5 milliliters. Because based on the density, that 17.5 milliliters would weigh 25.9 grams. Okay. So here we start off with volume. We multiply by the density to give us units of grams. Next question here is we want to know how many milliliters would 0.0735 grams of chloroform occupy. Okay, so we're looking for units of milliliters. So I set that up. That's what I'm looking for. That means in the numerator, milliliters will be on top, obviously, because that's the units I'm eventually going to get, and grams in the denominator. Okay. And so now it is 1.48 in the denominator. And numerator has 1. Okay. Check my units, grams cancel, leaving me with units of milliliters. So I now got it set up properly. Okay. So this means that if you weigh out 0.0735 grams of chloroform, it would have a volume of 0.0497 milliliters. And again, keep track of your Sig Figs. Density is not an exact number, it's a measurement. So density conversion factors could play a role in the Sig Figs, okay? All right. All right, we're going to shift gears just for a little bit and then kind of close up this chapter up. We got about 15 more minutes and we'll be done with it. So those are density questions. Okay. And we're going to just kind of touch on energy for a little bit / temperature. They come hand in hand when you think about it. When you put energy into a system and you measure its temperature, it goes up. Okay. And that energy is being absorbed by the atoms of that material that you're putting energy into the system. And like anything, when you put energy into the system, it tends to move around because it has high energy. I equate it to being on the beach on a hot day, you're barefoot. Okay. You know, so that sand beach is nice and hot and you're barefooted and you want to go from point A to point B. Well, I almost guarantee you that you're not going to walk nonchalantly on that hot sand. You're going to run, okay, because that heat's going to make you move. So hot molecules tend to move faster. They will. They don't tend, they do, because they have high energy, okay? Whereas cold molecules will slow down because their energy is a lot lower. Now, one thing to remember by energy, because we're going to touch on this again, time and time, that Mother Nature being Mother Nature, that energy always goes from a high energy state to a low energy state. And all molecules eventually are going to get to their, what we call the ground state, the stable state. And so molecules don't want to sit up there at a high state. They want to release the energy and get down to a more stable state, to the ground state. Now we measure obviously temperature with thermometer. okay? And we have two types of thermometers. We have the Fahrenheit for the English unit, and we have the C for Celsius, the metric, but we have one more, and that is the K thermometer for Kelvin. Now, they differ quite a bit here, in that Fahrenheit and Celsius go, value-wise, go to infinity in both directions, okay? We're gonna have an infinite number of degrees in Celsius and Fahrenheit in both directions. However, Kelvin does not. Kelvin stops at 0. Okay, we call that absolute 0. And it's based on Lord Kelvin. Kelvin was a British scientist, Lord Kelvin scale. It is proposed that at 0 Kelvin, absolute 0, all matter completely stops moving. You know, even when we're down to those low temperatures, that atoms themselves are vibrating in the bonds that they have. But supposedly down there at 0, everything stops, even that stops. We have not obtained that. I've not read anything lately about that. We come close to it. And the fascinating thing about that low temperature is, there's a whole new chemistry going on down there, whole new physical properties going on. So let's see if anything new comes up. Now, the other thing about these scales is the following. Celsius and Kelvin are connected. We can go from Celsius to Kelvin or from Kelvin to Celsius. However, we cannot go from Fahrenheit to Kelvin, unless we go through Celsius first. So if you got Fahrenheit, you got to convert to Celsius, and then from Celsius convert to Kelvin, and vice versa. If you got Kelvin and you want Fahrenheit, you got to go through Celsius and then convert that to Fahrenheit. So how do you do that? Well, on the shapes table, you have a couple equations that are given to you. You don't have to memorize it. And that is the conversion equations for Fahrenheit to Celsius and Fahrenheit, excuse me, from Fahrenheit to Celsius and from Celsius to Fahrenheit. Okay. If you have Fahrenheit, you subtract 32 and divide it by 1.8, that gives you Celsius. If you have Celsius, you multiply it by 1.8, and then you add 32 and it gives you Fahrenheit. Okay. Once you have, so I can go, once I have Celsius, I can go to Kelvin by simply adding 273 from to Celsius, and that puts me in Kelvin. So with that in mind, try this at home. 150 degrees Fahrenheit, convert that to Celsius, and then convert that to Kelvin. Try that at home. You should come up with 46 Celsius and 319 Kelvin. Okay. All right. Now, heat/energy. You got the question here. It says, which of these two beakers has a higher temperature? Well, it's kind of a trick question because you look like you have a beaker, a container, A and B. It looks like that red stick is a thermometer because of your temperature there, right? And guess what? They're both at 100 degrees. So, you know, both of them at the same temperature. The other aspect to take away is it looks like A has a lot more material than B. Okay, so there's more material. So the next question is which one has a higher amount of heat? All right, and that would be A. Now, why would A have a higher amount of heat? Who can tell me that? As we get closer a little bit here. Okay, another way to look at it is this. Okay, let's say you're heating up a big old pot for spaghetti, big old giant pot. Okay, and you're also heating up a little small pot for maybe a cup of tea or something. All right, and they're both boiling, they're both water. And now you have to have a choice. Which one would you rather have spilled on you? The big old pot of spaghetti water or the little pot for tea water? Obviously, you don't want neither one, but if you have a choice, which one would you pick? The big pot or the little? No, anybody there? The little one, of course, right? Because there's less water, less material, less atoms of water, and therefore have a smaller amount of heat/energy. Okay. If you don't know about El Nino, La Nina, it's out there in the Pacific. It's a body of water. That's all it is. Some people tell me it's a little kid. No, it's not a little kid, little boy, little girl. It is a body of water, which they name El Nino and La Nina. The difference is El Nino is a larger body of water than La Nina. It's out of the Pacific. And what it does is body of water has this temperature difference of only a few degrees relative to the rest of the ocean. But that body is so large that has a lot of energy, so much that it affects the world weather. Okay, so a lot of energy packed in here. All right. Now, when it comes to heat transfer, as I stated, always going from high to low. So in this case, heat transfer always 100% high temperature to low. Can you reverse it? Yeah. But you got to put energy into the system. Now, equate it to climbing a big hill, big, tall mountain. You're going to put a lot of energy to get to the top of that mountain. But you're going to do the gravity to come down that mountain. It's going to be a free fall and it won't take a lot of energy to come down the mountain, right? It's all downhill. That's how energy is. So it goes from top to bottom. So if you take up, for example, in this case, a cookie, take it out of the oven, what loses heat as you take it out and put it in your hand, that would be the cookie. It's hot. And what gains heat would be your hand. So you're burning yourself because that heat transfer. Another way to look at this is personal experience. You're in there taking a nice hot shower, nice cold morning. You're in the shower, got the water up high, nice and warm. You're equated with the temperature of hot water. You're done with the shower. You open the door. You step outside. You get cold, right? So what do? You jump back into the shower, close the door, and warm up a little bit. So what's happening here, as you're in the shower, your body is equated with the temperature of the hot water. Outside the shower, the temperature is lower. So as you step outside, you are at a higher energy state than outside the environment. So you lose energy coming from you. You get cold, right? So and now your temperature drops. So now when you jump back into the hot shower, that temperature in there is warmer than you now. So now the heat temperature transfers back to you and you warm up again, right? Eventually, everybody equates, you find some ground state, depending on your environment, to some room temperature. But if your room temperature is 0 degrees, that's where you end up being. Depends on your environment where you're in. Okay, so another example would be a piece of metal placed in the freezer. It's nice and cold. You take it out, put it into a bucket. Okay, the temperature of the metal will increase. Why? Because it's gaining heat, and the temperature of the water will drop because it's losing heat. In fact, if you ever need to lower the temperature of, say, a cup of coffee, it's pretty hot, or tea, just put a spoon in it. Put a cold spoon in it. Okay, that temperature would drop real quick. Common sense. I mean, I'm sure you're aware of that. I'm not telling you anything, something that you don't already know. Also, too, that same cup of coffee, once it could be boiling, but you leave it in a countertop. You come back an hour later, it's no longer hot, right? Because the temperature dissipates to the environment. It won't stay hot. All right, so you got your exam next week. All right. Don't forget there's more YouTube videos from Dr. Kim, plus the ones we record here. Don't forget about the Sig Figs. The Sig Figs, the rules significant figures will continue throughout the semester. And just put this in your mind, any calculation that you do, you will always use significant figures, okay? Don't forget your assignments and your homework and so forth. Next week you have, I think I sent an email, but it's about 24 questions for the exam. All multiple, most of them multiple choice. There are some fill in, give an answer to the calculation, give the correct answer. And it's open for a time period. You're given 75 minutes to complete it. By all means, don't wait until, close to shutdown, because campus will kick you off. So give yourself plenty of time, all right, to complete that exam. And don't overthink the questions. We're not trying to confuse you. And I try to be straight to the point to the question. Occasionally, you might have a question you got to think about. And that's the whole idea, to get the gears rolling, okay? All right, well, congratulations. We are done with chapter 3. And we will begin with chapter 4 next time. It will get us back on Friday. Next Friday, it'll get us back into chemistry. But remember, if you have questions next Friday, by all means,